Okay. So now we're going to take a look at Ohm's law and power as well. One thing I do want to point out in the notes from last time, so you might just want to make this little note here. Okay, the Ohm, the symbol for Ohm is the Greek letter omega. Okay, and that's always a fun one to do. So anyway, let's move on and take a look at Ohm's law. Okay, the basic idea of Ohm's law says that for a particular device that we call ohmic, okay, an ohmic device, if I connect it to a battery, some sort of battery here, okay, and some sort of ohmic device, and I connect it to the battery here. When I turn this on, okay, when I flip the switch, there we go, I'm going to switch, a little fancy. When I flip the switch, I'm going to get a current that flows through. Now, let's say I can vary the amount of, vary the voltage, okay? An ohmic device, for an ohmic device, as the voltage goes up, the current goes up. As voltage goes down, the current goes down. Okay? And we can have things that have a negative voltage. Basically, we're looking at it backwards. Okay? So we could, if you want to take a look at negative voltage, you just put the battery in backwards. Okay? And you still go around the loop in the same direction. So now, as voltage goes down, the current goes down. As voltage goes up, current goes up. If I graph this out, made a graph of voltage versus current. It doesn't have to be 1-to-1, okay? But it has to be a straight line, okay? And it would have to go through the origin. And that's why we say that the current is equal to the voltage divided by the resistance. In order for this equation to hold true, or V equals IR, however you want to arrange it, in order for that equation to be true, this has to be, you have to get a graph that looks like this. In actual facts, to keep it looking like that, even though current really is the dependent variable, depending on, well, I guess it depends on how you set it up. It's, we get a straight line like this. Now, examples of things that are purely ohmic devices. Okay, when we deal with, or that we can treat pretty closely to an ohmic device. Okay, anything that basically heats up when we connect it to a battery, all it does is heat up. That's what a resistor does. It heats up. Light bulbs. We treat as an ohmic device. Yes, some of the energy is lost to lighting and everything like that, but it is that light is created through the heating, and so we get so anything that, like your toaster oven, okay, any type of electrical device, like electrical oven or anything like that, is more or less an ohmic device. Not exactly, and actually. The curve does deviate from this because as it heats up, okay, the resistance changes as well. So we have to be a little bit careful about that because, like I said, because it does heat up, you know, the resistance does change. Now, examples of things that are not ohmic. We have things called a diode. Diode is really simple. If you plotted the voltage versus the current here, you get something that looks like this, okay, and it would go up like that, okay. There's basically no current for a negative voltage, and this would be for a particular type of diode. This is an example. And then the current would go off and explode. And then from there, you have transistors, you have integrated circuits. Most devices are not going to be ohmic. Capacitors, not ohmic. Inductors, not ohmic. Okay, but resistors that we use are very ohmic. Okay. Again, what defines an ohmic device is something that follows Ohm's law. Ohm's law, by the way, I don't think I specifically said this. This is Ohm's law. A device is ohmic if it follows that law, which, okay, good enough. So now it says a conducting material obeys Ohm's law when the resistivity of the material is independent of the magnitude and direction of the applied electric field. Really, we want to focus on the other one, where it says a conducting device obeys Ohm's law when the resistance of the device is independent of the magnitude and polarity of the applied potential difference. Okay, so in other words, the resistance is not affected by the current, okay, or by the voltage. I'm not going to get into the microscopic view. Just want to talk about power here for a second. So now we have from before power. With power comes great responsibility, but also we know that the differential amount of work that's done is equal to dq v, assuming a constant potential difference. Now, we also know that I is equal to dq over t, so I can rearrange that to be dq is equal to I dt. Okay, just rearrange this, put it over there. When two equations are very similar, they're just kind of rearrangements. A lot of times you'll see, especially next year with the professors, a little equals arrow sign. It's not really equals, but they're really very closely related to each other. So now, that differential amount of work is equal to I dt times potential difference. We'll do it with respect to time. So now du dt, which is power, is equal to the current. Now, this is one of those things that we can rearrange a little bit. When you're dealing with the power, this is usually how we look at the power output of the battery. Okay, how much current is coming out of the battery times the potential difference of the battery. Now, when we start talking about the power being dissipated by a resistor, okay, usually we want to focus on the current going through the resistor. Okay, and so we know power is equal to IV, but we're not looking so much at the voltage of the resistor. This is going to equal current times resistance. A lot of times we know the current, we know the resistance directly. So I would plug in this for the voltage. So I times IR gives me I squared R. Or I can look at it in terms of, I can plug in for I this time. Okay? Because a lot of times you don't know what the current is. Okay? You know what the voltage across the resistor is, you know what the resistance of the resistor is. So now I is equal to V over R. So now I plug that in. V over R times V. And so my power is equal to V squared over R. Just a couple of final quick things that we want to talk about. I don't know if it's pretty good. I know I've mentioned it last year. They talk about semiconductors and the like, but I do want to be able to use these symbols. I know that I've talked about battery again. So symbols that we have so far. This is the battery. Okay, our capacitor looks like this. Now, we have the resistor. Okay, got to be a little careful because it starts to look a little bit like an inductor, which is something that we have coming up a little bit later on in the year. That's pretty much it for chapter 26. Your homework. I know you guys have a test to study for, but things that I want to go through. Let's go 1, 2. So chapter 26. So chapter 26. 1, 2. I'll do 1 on T7. Let's go with, this is where the more interesting aspects are coming from. 15, let's go with 20, 24, 1, 2, 3, 4, 5, 6, 7. And then, so a lot of those are pretty, very, very fast. So I don't want you guys to really go through those. And then we'll go to 37, 44, and 47. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, I know it's 10 problems. 4 of them take like 30 seconds each. So I don't want to hear one in his class. All right, I will see you on Wednesday.